Okay. Last year, you guys did a unit, and this group right now, pre-calculus, they're testing on this. They have something like, say, y is equal to 2 to the x, and you have to graph that, and so this is just a 2-second review for you, but do you remember that the graph looked something like that? Passed through 0, 1, and had a horizontal asymptote of y is equal to 0. And then, if you flip that over the line y equals x, you get this shape. Passes through 1, 0, and has a vertical asymptote of x equals 0. And that is the graph of y equals log base, say, 2 of x. So on Friday, we talked about inverse functions and their derivatives. Well, today we're going to talk about a couple of functions that have inverses. And you maybe don't remember what a logarithm is, but I'll try to show you real quick. Suppose you had 2 to the x was equal to 40. Do you know what power you take 2 to get 40? I don't either. So I'm going to get rid of the base of 2 by taking a log base 2. Remember doing that? So those went away. X is equal to log base 2 of 40. And so you did log of 40 divided by log of 2 on your calculator, and that told you the power. Or maybe you had this. Maybe you had log base 3 of x is equal to 30. And, well, let's do something. Let's do like 1.5, 1.4. You know, so you were wondering what would solve for x. So you created a base of 3, and those went away, and you got x is equal to 3 to the 1.4 power. So you remember kind of a little bit of those operations last year? These are very important functions, and last year some of you saw a special number called e. We looked at y is equal to e to the x, and some of you spoke about your distaste for e. In fact, when you saw a natural logarithm of x, you're like, what the heck is ln? And why is it nl? And it looks like an I. And I actually had students up until Friday, they were still writing that, in, every time they were seeing natural logarithm. They thought it was an I. I was like, it's not. They got mad at me, but whatever. So E is a very, very special number, and so I'm going to do one demonstration for you, and then we'll move along to our lesson, but try give you a little bit of an idea of why this comes up. I'm going to give my good friend Jonah some money, okay? Jonah, you get some money, okay? I'm going to give you $1,000, and we're going to invest it at a rate of 4%, and it's going to compound monthly. We're going to leave in the bank for 10 years. And that's the formula that could tell you how much money you're going to have after it's been invested for, 10 years. And we played around with formulas like that. Well, if we just change this formula a little bit, suppose we just invest $1, and it compounds not at 4%, but at 100%. And it's going to compound a certain number of times over the given course of the year. I want you to take that and type that into your calculator into the y equals. So I've got 1 plus 1 over x raised to the x power. This gets kind of cool here. So what's that? What that's just talking about is some type of rate, okay? And it's going to compound a certain number of times throughout the year. So what I'm going to do is I'm going to go to my table, and I'm just going to compound it once. So it'll be 1 plus 1 to the 1 power, which is just 2, right? Suppose I'm going to compound it semi-annually. How often would that be? Twice. 2.25. How about quarterly? Monthly? Weekly? daily. What's happening in the numbers? They're not increasing by very much anymore, are they? Well, how about every second? That'll be 365 days, 24 hours a day, 60 minutes an hour, 60 seconds a minute. You know what number that is? That's E. E is that limit as x goes to infinity. Comes out to be 2.7183. It models when we have continuous growth. For example, bacteria growing on your calculator and your phone. Okay, so there you go. All right, so let's deal with E. So if you didn't like E before, hopefully you'll like it now. It's pretty awesome because when you take the derivative of e to the x, you get e to the x times the natural log of e. Darren just said it. Do you remember what the natural log of e is? It's 1. So in other words, the derivative of e to the x is e to the x. It's a special function. The derivative of it is itself. Suppose you don't have a base of e, or 2.71, so on and so forth. Suppose you have a base of b. Then you get b to the x times the natural log of b. So suppose it was 2 to the x. The derivative would be 2 to the x times the natural log of 2. Y'all good? All right, let's try some problems. Find the derivative. What rule do we use? Product. And I get 3x squared times e to the x plus x to the third times what's the derivative of e to the x? E to the x. Isn't that nice just to say it? You can leave it like that, or if you'd like to factor out an e to the x and leave 3x squared plus x to the third, you can do that as well. Here's something that's a little bit new for you with letter B. Some of these you don't have written on your sheet. I realize I think I added D, right? So you could just add them as we go along. I apologize about that, but as I was looking through the notes last night, I wasn't satisfied with what I had. So f of x is equal to e to the 4x squared. I'm going to use a chain rule, and my function on the outside is going to be e to the u. So what would the inside be? 4x squared. Derivative of 4x squared. And derivative of e to the u. Therefore, f prime of x is 8x e to the 4x squared. Notice that what's out front is simply the derivative of what we have here. That will always be the case for e. What we have out front here is the derivative of the exponent. Makes it pretty simple when you're doing some other problems. See what rule? Quotient rule. So f prime of x will be equal to derivative of the top times 2 minus x minus the derivative of the bottom. This will be a plus e to the x over 2 minus x quantity squared. Well, we could combine like terms now, couldn't we? So it'd be a 2 e to the x plus a 1 e to the x would make a 3 e to the x minus x e to the x all over 2 minus x. Oh, smartboard got stupid. Okay. Um, if you wanted to, you could factor again the e to the x at the top, and that way, if you do, you can see right away that this has an x-intercept at 3. It has a vertical asymptote at 2. It's kind of nice. So. What's different about letter D compared to the problems we've done? There's no e. There's a base of 5. So treat this like I did the one above. I'll say 5 to the u, and I'll say 3x minus 2. So we'll do the easy derivative. Derivative of 3x minus 2 is just 3. What is the derivative of 5 to the u? 5 to the u times natural log of 5. So this is the first year where I've tried to explain it like this, that the derivative of e to the x is e to the x natural log of e, because it just goes away because it's 1. So it's always there, just it simplifies and goes away. So a lot of times people forget that natural log of 5 piece, so try to remember that. So I just bring this out front. I've got 3 times 5 to the 3x minus 2 times the natural log of 5. What mistake do you think people might make when they try to simplify this? Yeah. 3 times 5, they say, is 15, and that's entirely incorrect. So, well, 3 times 5 is 15, but, it'd be like, say 3 times 5 squared. So you're just going to ignore that the order of operations says we have to square it first. And you're just going to take 3 times 5 is 15. If it was 3 squared times 5 squared, then it would be, then you could do 15 squared, but it's not like that. Okay, letter E. Most challenging problem that we'll see today is letter E, but I want you to see one that is going to press us a little bit because you already get all this. It's way too easy for you. What rule do you think we use? All right, let's do the chain rule. E to the u, 3 sine cubed of the root of x. I know that's e to the u, but I'm not so sure about the derivative of 3 sine cubed of the root of x. Thoughts? Chain rule. And here's where we got to be really smart, folks. What sits on the outside and what sits on the inside? What everybody says. Does the 3 really matter? The first one? It's just a constant, right? So think about sine cubed of the root of x. Think about our operation. We plug something in for x. What's the first thing we do? Take the square root. And after we take the square root, we then... I've already rooted it. Then I take sine first. This means sine of the root of x, that quantity cubed. That's what that means. So what's the last operation? Cubing it. So that's what I put on the outside. I have a u cubed, and it's multiplied by 3. So what sits on the inside? Sine of the root of x. Okay, derivative of 3u cubed is 9u squared. Derivative sine of the root of x. Uh-oh. Chain rule. Cheer Wally. He's like, what's going on, dude? This ain't right. It should be a law against this. Cosine of u. Good. 1 over 2 roots of x. So if we multiply those together, we get cosine of the root of x over 2 roots of x. Now I got to multiply these two together, don't I? I get 9 times sine squared of the root of x times cosine of the root of x over 2 roots of x. And then I've got to multiply these two together by plugging this back in there. So looks like I'll end up with 9e to the 3 sine cubed of the root of x times sine squared of the root of x times cosine of the root of x all over 2 roots of x. Sure. Maddie's shaking her head. Sure, that'll be sweet. Try F on your own. Go. Two times x times 3 to the 4x. So as you set it up, I would make this F, and I'd make this. I do the product rule if you haven't noticed that already. I'll slowly start working it out for you. Yep. Questions, how do I get the natural log of 3? I have 3 to the u. I have 4x. Derivative of 4x is 4. Derivative of 3 to the u is 3 to the u times the natural log of 3. How's that? Everybody get the whole thing? Where'd you make your mistake? You didn't do the chain rule? Gotta use the chain rule for the derivative of 3 to the 4x. Now you do. We're smarter because of it. Let's flip it over. What do you think I set up for G? So I have the square root of u, and on the inside I have 4 minus e to the 4x. 1 over 2 roots of u. Yeah, you do, but maybe you've noticed now that when you're doing the derivative of e to something, you just take the derivative of the exponent. So the derivative of 4 goes away, but the derivative of 4x becomes, yeah, we just have it's a negative 4 e to the 4x. And if you set up the chain rule there, you're going to come out with that. So now we just multiply these together. When we multiply them together, what happens? Yeah, So the negative 4 and the 2 become a negative 2 in the numerator. So negative 2 e to the 4x over the square root of 4 minus e to the 4x. Because a negative 4 times 1/2. Any other questions on that one? You for sure get through f. F's no big deal. We'll treat a as a constant. X is our variable. Secant of e a pi x. E to the a pi x. So got here, what's my outside function? Secant of u, inside function. Derivative of secant. Secant tan. Derivative of e to the a pi x. A pi e to the a pi x. If you were to set up the chain rule, you would say it's e to the u, and it's a pi x. The derivative of a pi is just a constant. So this is just referring to the slope of that line. So you get a pi. Derivative of this is e to the u. So you get a pi e to the a pi x. Now I just write it all multiplied together. So f prime of x is a pi e to the a pi x. Secant of e to the a pi x times tangent of e to the a pi x. There you go. We got 2 more problems when you get back, and you will have your worksheet, just the front and back. Go get some brain food. I used to have a thermometer, but all right, let's move to letter I, and then we'll do our last problem, which will be problem H. I do have a scissors. Okay. So problem I says x times 4 to the ax minus 1. Does anybody see the rule that I'll set up first? Product. Derivative of x times 4 to the ax minus 1 plus x times, how do I find the derivative of 4? Yep, chain rule. You guys are so smart. Just imagine how the Eskimos feel. Like the Eskimos right now, they're having class in an igloo. All right, derivative of ax minus 1. A. Derivative of 4 to the u. Very good. All right, somebody ate their Wheaties today. Nice job. Okay, anomaly. Times a times 4 to the ax minus 1 times natural log of 4. If you want to factor out the 4 to the ax minus 1, you can, and you get 1 plus ax natural log of 4. So okay, last one, H. I want you to know that as I've been looking for consistency within kind of textbooks and answer keys, it appears that many textbooks do leave a negative exponent if there's a variable. So, for example, we wouldn't want you to write 2 to the negative third and leave it, nor would we want you to write x to the negative 2 and leave it, but 2 to the negative x, that would be acceptable. Okay? Well, I'm just saying you could write this as 1 over 2 quantity to the x, but instead of writing it, because either way you're going to end up with an issue. You see that? So, all right. Um, so let's. What rule do we have to use? Quotient rule. And when I take the derivative of the top, again, taking the derivative of e to the x is not going to be that big of a deal. But e to the 4x, good, 4e to the 4x. So if we were to set up the chain rule, we would have e to the u, and we would have 4x. So you always just end up taking the derivative of the exponent. So derivative of e to the negative 4x. Times the bottom minus the derivative of the bottom, derivative of the, or top left alone, e to the 4x plus e to the negative 4x. All over 16x to the 4th. What's going to happen? What cancels? I could take a 4 out, and I can take an x out, right? So 4e to the 4x minus 4e to the negative 4x times, if I take out a 4x there, I'm left with just x minus 2 e to the 4x plus e to the negative 4x all over 4x cubed. If you multiply the x through, multiply the 2 through, there's really nothing that is going to combine together. They're all going to be separate terms, and so we're okay just leaving it like that. Everybody good? It's a great day. Derivative of e to the x is e to the x. Doesn't get any simpler than that.